Okay, good morning, everyone. Welcome to this session. It's my pleasure to introduce again Richard Aoun, who will continue his crash course on random matrix products.
Thank you. So we stopped last time in proving Furstenberg result about unique existence of unique stationary probability measure on the projective space under these assumptions: strong irreducibility and proximality. The example to keep in mind: gamma mu equal SL2Z, and mu any probability measure on any supporting generated set, or more generally, a non-elementary subgroup, let's say, of SL2R. By non-elementary, we mean non-compact, and we do not fix neither a point on the projective line nor a finite 2 points. I do not permute finitely many points. Do not fix finitely many points on the projective line. So this is an example in dimension 2. This is really the guiding assumptions. So I do not, my subgroup is not consisting only on parabolic elements. My subgroup is not like the Kiefer's counterexample because I permit 2, and I'm not rotation. So I contain lots and lots of hyperbolic elements. Okay, these are these two basically assumptions. Are there any questions about the assumption before I begin the proof? Because my goal is really to spend time with the proof because it gives a lot of ideas of what happened later. Okay, so the proof is by steps. So I will begin with step 1. This is general. By general, I mean it's not strongly irreducible and proximal. And I think this is really the start. So I will put Furstenberg and Guivarc'h Raugi, and I will be clear what's happening. You have a topological group acting, let's say, on a compact metric space. And you have a probability measure on G. You have a probability measure on X, which is mu stationary. Alors, this already implies something on the trajectories of the random walk. Then, let me put it like that. Then, almost surely, your random walk, but in this order, from left to right, B1, Bn. Before I was considering Bn, B1. Pushes mu on a probability measure, which is random now, depends on B. So this is a random probe. It exists, okay? This is part of the result. Probability measure on X, a random probe on X. So for almost every infinite sequence, I have something happening with the random walk. My initial data is mu and nu, and the random walk at right pushes your measure to a random measure. In these cases, just to motivate, it will be a Dirac mass. With this assumption, we will prove that my measure will be pushed by the random walk on the right by a random direction. In general, this is this. And what is this new B? I mean, what is its relation with nu? I can reconstruct my measure nu by integrating over all the possible trajectories. And the very important observation of Guivarc'h Raugi is to say a bit more. Actually, this is a, let's say, probabilistic result. But actually, I can put here an element of the group. So it will tell me something actually. There is an information about the group and what is G. So for almost every beta and for almost every element G in the semigroup. And what is lambda? Lambda is some probability measure on the group that has full support. So the result is for almost every trajectory, for almost every element in the group, I have this. And before
you act in different order with B than at the beginning.
You mean if I put n here, there is no
You take some dual or just notation?
If we put on the left like this, suppose I have in my support element that does rotation, so I cannot converge. Because it's almost surely. It's action here, the left action is the geometric action, let's say, because I'm acting, so I cannot really converge because...
Because I have the intuition maybe when you act different directions, it's kind of ergodic study. And if you do like this, it is localization of what is happening. You will use martingale.
Yeah, exactly, and here I will use martingale.
This is I know it from somewhere, but...
iterative function system.
This is like...
Yes, exactly, yes.
So it is not jumping there and
This is not exactly...
there with dynamics, but it is localizing.
To do dynamical argument or Markov chain result, I do the left. When I wrote last time the log norm as a ergodic sum, it was the left. Now it's, yeah, exactly, yes.
Excuse me, the lambda is equal to tau, and what is in the exponent? Tau.
Sorry. So lambda is a probability measure, I will define it. And mu to the power I is the distribution of my random walk at time I. Left or right, it doesn't depend, I have the same distribution. What's important is that it's a probability measure supported on the whole group. It will help me say something about the group. To motivate the importance of this result, I will give a corollary independently of what I want to prove. Before proving, corollary Choquet-Denis, one way of proving the result I stated in my first lecture.
Sorry.
Yeah.
So the result is so this B1 Bn G mu tends to the same mu B. Sorry.
No, this is the new my initial data. I have a stationary probability measure on what I say. Yeah, on X.
No, but now you added an orange part, this G, right?
Yeah.
And it doesn't change the result.
Yes.
So it still goes to new.
Yes.
Okay.
And that will be what will be strong because I will choose many elements with different behaviors, and it will really give me some rigidity about this. What was Choquet-Denis? If I have an abelian topological semigroup acting on X compact, I said without proof at the beginning in my first lecture that nu stationary is the same as invariant. Really invariant under all element of let us see immediately in one line how does this result implies it. So from left to right, trivial. So from right to left, my initial data is new. Using 1 and abelian, all these are elements in the semigroup. I can put it. Because my AB, and this is an information for beta almost every trajectory for almost every element. But this, as you were saying, I mean, this also converges to mu B. Just take G equal identity. So I will have G mu B equal to mu B. Disintegrate now. This is an information. And this is for lambda almost every G. And this is a closed condition on G. Since the support of this measure lambda is gamma mu, this implies that I started with a stationary probability measure, and I showed that it's invariant under the semigroup, not only in average. Stationary mean invariant and average. Here I prove it invariant. And since it's abelian, I can just put G here. So let me prove, do you want me to prove the result of uniqueness using this first or the opposite direction? Is there any preference? So let me go with the proof, since we saw that it can be useful. So as you said, it's a Martingale result, technique. So proof of theorem 1. In my first lecture, when I introduced stationary probability measure, I also used the word harmonic. But I didn't, why? So here I will use this observation. If you have a mu is fixed on G, so mu stationary on X. This is one data, and the other data, a continuous function on X. Given these two data, I can construct a function on my group by acting on the element and then integrating over the mu. So G is fixed, and this gives me a mu harmonic bounded function, I'm supposing X compact, bounded function on G, bounded mu harmonic function on G. What do I mean by mu harmonic? So with respect to the action of the group, the value at a point in the group is the average near your G, near with respect to the right multiplication by an element of the group. And this is really just from the definition of stationarity. Indeed. So from here to here is really the definition of stationarity, and you can think of it as invariant under average. This is the best way to see from where I go from here to here. G is fixed from the beginning. Okay? Are there questions or clarification? And what is the consequence? A consequence. I look now at the process, the sequence of random variables. So f, I fix f now, continuous function. I look at this process. So I fix a function, continuous function on the geometric space, and I consider the sequence of random variable. And saying that this function big F is harmonic on the group implies that the conditional expectation of f of b1 bn plus 1. Let me write it here because this would be. Conditioning by the sigma algebra generated by the first n coordinate. So knowing what are the values of your first n step of your random walk, what is the expected value of big F, since it's IID, independent, just the integration of B1, Bn, and this now can vary over mu, h, d mu h, and since f is harmonic, this is big F of b1 bn. So I have now a process. So I have Mn process such that expectation of Mn plus 1 over sigma algebra is Mn. And this process is uniformly bounded by such processes are called martingales. This is a generalization of an IID random walk. And Dub's martingale result theorem tells you that with these two assumptions, your martingale converges almost surely with boundness, or more generally equi-integrability, uniform integrability in L1. So definitely I need 1 and 2. A martingale is a fair game. Knowing what's happening in the past, the expected value is the previous random variable. This is an equality almost sure. The conditional expectation is a random variable. So what do I gain? Let me rewrite what I obtained. F of B1 Bn dot x d nu of x converges for beta almost every trajectory B to a function of f, and it's a functional. And the quantifiers is for every f. This holds almost sure for beta almost every B. Since my space is a compact metric space, the space of continuous function on X is separable. You have a countable dense set. So like we saw in the first lecture of John when showing existence of generic measures, I can now intervert the quantifiers, and by a density argument, I will obtain that almost surely for every f in C of X, I have this convergence. So this is a really very weak convergence. So this functional must be given by a probability measure. Because when I act on every function by this measure, I obtain this. Now, why this functional is given by d nu b? Either I use Riese representation, or I take a weak limit if I want, and I deduce that all the weak limits must be the same because it converges to this. Okay, and a word about this G. I will be quick, but this is the G which is important. Now I prove this, but how I prove was inserting this G here, with G in the group, and this was really important. So how I will put, so I basically finished the theorem, except with the G. I will erase here, but write only. Let us look at let me integrate. Big F is the integral with small f. Which, big F was the martingale that converges. And actually, I want to show that this goes to 0. Okay. If I show that this integral goes to 0, I will obtain that for almost every g with respect to mu, the inside converges to 0. And they will have the same limit. Okay, it's not enough. Actually, I have to put lambda here because I don't want only to integrate with respect to the support, with respect to square, etc. But let us just see what's happening with mu. So I will show step 1.1. Let's show that this goes to 0. And this will imply that almost every g, what's inside the integral goes to 0 almost surely. And this, we proved already that it converges to integral f d nu. This was proved. Again, martingales. This quantity, we'll call it In, can be interpreted as the expectation at step n plus 1 because I'm integrating over g. I don't want to write it with integral over beta, but I mean it's okay.
Why square?
Thank you. Thank you. I want to prove this, but I will not know how to prove it, so I will prove this. Thank you. So, yeah, there is some L2 going on. And so this is a martingale, Mn plus 1, this is Mn. And martingale just means that expected value of Mn plus 1 over what's happening in the past equal Mn. And our martingales are bounded, so they are in L2. So I can use the interpretation of the conditional expectation as a projection. So I'm working in L2 of B sigma algebra beta. This is the subspace L2 B Fn beta. Mn is measurable, belongs to here. Mn depends on n. So my Mn, I see it now, the random variable, I see it as a vector in L2. Mn plus 1, I know that its conditional expectation with respect to this sigma algebra, that actually this is n. Hence, Pythagoras, expectation definitely I don't need, by computation this follows, but I wanted just to, if you haven't seen martingales maybe before, I don't know, so just this is what happens. But my random variables converges, even in L2, bounded. So this is expectation of gamma f minus expectation of gamma f. It is 0. And that's it. And what's remaining to do it not only for mu, for mu2, for mu3, etc. It's not so hard anymore. It will not be Mn plus 1, it will be Mn plus 2, Mn plus 3 with S. Fill the details. To prove it algebraically, this we just use the power property of the conditional the Tower property of the conditional expectation. Okay. Questions? And now let's prove the theorem. Before the theorem, a lemma that I won't prove because I don't have time. Step 2, lemma. Less general than here, but more general than the initial conditions. So now I'm working with matrices. And I assume that my action is strongly irreducible, but not necessarily proximal. Okay? Then any mu stationary proba on the projective space is non-degenerate, which means in this context that it gives zero mass to any projective subspace. Proper. Here I'm doing an identification between RD and PR. Let's say this is P of E. So for n, it does not give a positive probability on a subspace. I didn't say invariant, because if I assume nu to be ergodic, for sure it will not live on a proper invariant subspace. I will not give the proof, but definitely some remarks and intuitions. If I'm acting irreducibly, it means that I'm stabilizing a subspace. Okay, so I cannot expect to have for any stationary probability measure to give zero mass. So if I stabilize a subspace, I act here. I act on the projective space of this subspace, so for sure there are stationary probability measures here, like the example of affine with Dirac E1. Now, why strongly irreducible? Because here we don't see that there is a finitely many things happening. Let's go back to the counterexample of Kiefer. It was irreducible, but with Kiefer example, counterexample, this was stationary, but irreducible, not strongly. And I give positive probability to E1 and positive probability to E2. They are not invariant. But I give positive probability measure on a proper subspace. So yes, there is something about not the assumption of not preserving a finite union of subspace is necessary. Okay? Questions? So now let us prove the theorem. The uniqueness. Proximality was not used now yet. Now it will be used. So we assume that gamma mu is strongly irreducible and proximal. And I want to show that there is a unique stationary probability measure given mu. So what I do, I start with a probability measure. I know by compactness that exists, and I will describe it. I will tell you this is its formula. Let nu be mu stationary. And I will tell you what it is qualitatively. By step one, the Martingale theorem, I know that B1, Bn, G nu converge to some probability measure on the projective space, or beta times lambda almost every infinite trajectory, comma g. This is on the one hand. On the other hand, I will look at my projective action. I take my product of matrices, B1, Bn, and I normalize it, just to see how it acts projectively as a matrix. It has norm 1. So I'm working in a compact subset of D by D matrices. I can find a subsequent, I can find a limit point in the space of matrices. And K is random, okay? Gamma B. Let me call it PB. PB is no more invertible necessarily. So just the intuition is, I take a hyperbolic matrix, I take its power. We saw last time, here it's trivial, and we saw last time that it will converge to a projection matrix. This will be my P, okay? So I'm doing this randomly. Just to see what's going on. Now B1, Bn is in an invertible matrix. I normalize it by norm. I will have a sequence of endomorphisms living in a compact subset of endomorphisms. So there is a limit. So PB not necessarily invertible. And I will show that it has rank 1. That's one of the things, is I will show that it's of rank 1. This PB, like here. But not necessarily a projection. Okay, what I will do, definitely here it's a topological. I can put here G for any G. And now I will push forward bar nu. This is not necessarily true that I can put I want to do this in order to identify with my, but this is really well defined because these are invertible matrices. I act on the projective space, but this is no more in PBG. Even PBG is not 0, okay? Because PB has norm 1. PB has norm 1 and G is invertible. But mu can be stuck in the kernel of PBG, so I cannot really define this measure. But that's why this is true, because by step 2 lemma, mu is non-degenerate, so mu gives 0 mass to the kernel of PBG, which is a proper subspace of RT. So I can pass to the limit. And this condition is closed in G by non-degeneracy of my measure. It means if I have now a sequence of guys like that converging, I can also pass to the limit. I have continuity for the push forward because of this. Again, mu non-degenerate. I will have for beta almost every B and for all G and and the quantifiers are important for any trajectory, for any element of the group. And this is strong. This is really strong. Okay, and the idea now is I want to play with the G's. I am proximal, I have lots of hyperbolic elements. So I take G with a matrix like 2, I'll have 2 to the power n, 1 over 2n, etc. G will converge to a rank 1 projection. PBG will be stuck to be, will have rank 1 or 0, but it will have rank 1. So I take G, I will do another limit, but G a proximal element, attractive direction. It's pushing everyone in the projective space to a direction except a bad subspace. I have PB endomorphism, okay? So PBG will be another rank 1 matrix. And I'm pushing, so I will push knw a point to a one direction. That's the idea. Take G proximal. So G to the power n over known to Gn via subsequence will converge to a rank 1 projection. I can apply my equality applied for every n will give me PB Gn nu equal to nu b for any n. And I want to pass to the limit. To pass to the limit, it's a bit tricky. 2 cases. If PB, so take 2 cases. If PB gamma is not 0, generally it's like that. I can define by non-degeneracy. I will have PB gamma nu equal to nu b. Gamma is rank 1, but PB gamma, the image of gamma can be in the kernel of PB. But now this has rank 1, I don't know its rank, but the product is of rank either 0 or 1, but it's not 0, so it has rank 1. And nu, by non-degeneracy, gives 0 mass to the kernel of PB gamma. Again, nu non-degenerate will tell me that nu b will be just the Dirac measure on the image of PB gamma, which is aligned. This is a point. So nu b is a mass, it exists, it's something, and nu, by the first lemma, it's integral. I described nu.
Sorry, I got lost. Why proximality implies convergence?
So proximality, you have implies
Convergence.
yeah.
So you were looking at the subsequence.
Yeah, here for sure, just because of signs, I should do subsequence, but
General limit does not exist.
no, if you take just -2 and just as this will, when I take to the power n,
I see.
yeah, just because of signs, yeah. Now what happens if PB gamma was 0? There are some issues of measurability that this random variable b gives that b is measurable in order to say that I describe it. And what happens if pb gamma was 0, which means that the image of gamma, which is a line, was stuck in the kernel? No problem, I use irreducibility. Since gamma is irreducible, I can always find an h that's such that h image of gamma is not. So here it's an binomial, it's not in the kernel. So the image of gamma is non-zero, this is proper. Irreducibility implies that you cannot send a line to a proper subspace. Irreducibility implies that you cannot send the line to a proper subspace by all the elements of the group. And this is image of H gamma. Gamma has rank 1, okay? It's a projection of rank 1, the rank 1 projection. So this is by irreducibility. What I do is I go back to the strong thing, to the bad phase. Okay, I do PB, H, G to the power n equal to nu b, because it was true for any element in the group. Now pass to element. And do the same argument. At the end, I'm saying that nu b is a point, so this point cannot change case 1, case 2. Nu b is here. By the strands of Furstenberg result, the sequence of measures converges almost surely. Nu b is here as a measure. So this ends the proof. So the z of b should be thought as an attractive point as if this random walk b1 bn becomes proximal when n tends to infinity. So it behaves like the power of intuition. b1 bn behaves like the power of a random of the power of gb to the power n with gb proximal. It behaves like the power of a hyperbolic matrix. It has an attractive point. Now do all your random walks, you will have many attractive points, and the stationary measure is just the support of your stationary measure is the collection of these points, and your measure is really how much I'm going back to the same attractive point. Corollary of this unique ergodicity, unique stationary measure, so unique ergodic, just to appreciate. Corollary, support of nu, I will call it lambda, is the unique gamma mu minimal subset of the projective space. So minimal, closed, and topologically transitive. So every orbit is dense and for sure gamma invariant by the semigroup. That's a very weird way of proving this. Why? Because this is a purely topological result. In which, if we look at this, gamma mu, forget mu, we're working SL2Z, right? I can find many generating set. Example, I'm doing an example. So suppose gamma is SL2Z, this is L2Z, there is no probe. I can change my measure mu, find different generating sets, different weights. I will have different stationary measures. But I'm saying that the support depend on the semigroup. So it's a topological result. So really this is not maybe the good way of proving it, and indeed we can prove it purely topological with assumptions from reducible proximal, just to do the link. So yeah, in the irreducible setting, at least proximal, there is some rigidity. You take your semigroup, no proba, take any measure such that it's non-degenerate on gamma. It means that the semigroup generated by your measure is this gamma. You have many stationary measures, many fractals, but their support is the same. Proof just by uniqueness. Let's say why it's minimal. So now mu is here. Okay. Why it's minimal? It's invariant. Always, it's not difficult to show that the support of the stationary measure is invariant. It's closed by definition of support. Why it's minimal? Well, if it's not minimal, there would exist a proper subset, which is closed, gamma invariant, in PV, in projective space. Hence, it's compact. So by the same procedure with telescoping sums, I can find a stationary probability measure. You remember when we act on a compact metric space, always we have stationary measures. There exists mu tilde supported in F, which is mu stationary. But it's not new because they have different support, contradicting the uniqueness. And also unique minimal, it's the same argument. Just a remark, I mean, what is lambda topology? I mean, as a description, is the closure of all attractive points of proximal element in gamma. Yeah, I mean, because we said that's independent of mu, so we need a description. You take all the elements in gamma, which has an hyperbolic behavior, you look at their the eigenvector which highest eigenvalue, it gives you a point and a line, it's a line. It's a line because it's proximal, so it gives you a line in the projective space, and this is a point, we take its closure. And this is maybe not closed because of many proximal elements converging to a rank 1, but not a projection. I mean, if I don't want to do a closure, I should say this is all possible limit Gn of G. Let's say gamma, such that the Gn are in the group, and gamma has rank 1, without saying that it's a projection. This is a closed set. All the rank 1 limits in the endomorphism. Great. So, for sure, I'm not sticking to the plan of giving you my result about what's happening outside the irreducible case, but to complete the picture, I will tell you just what happens in the irreducible and not strongly irreducible. And if you are interested, you can look at the paper with the Kagri cert, where we gave a description of stationary probability measure outside the irreducible setting. But just pedagogically, let us say now what happens next when I'm irreducible but not proximal. Irreducible, not proximal, like what? Let us take SL2C seen as a real group. So now, if I am irreducible and not proximal, let's say strongly irreducible and not proximal. Example, SL2C seen as a real group. Always you will have an eigenvalue coming with its conjugate and it will not be real. I mean, even if it's real, it will be of multiplicity. So here always the spectrum of an element will be lambda, lambda bar, mu, mu bar. So you will not have a dominant eigenvalue. Not dominant eigenvalue. We say that the proximality index is 2. Generically, mu and lambda and mu have different modulus generically, but always I'm stuck with the first and second. It's in a real group, so I embed it in SL4R. I'm embedding it in SL4R. This was studied by Guivarc'h, Raugi, and revisited lately by Benoist. So 2007, 16. And it will tell you in these cases, there is a one-to-one correspondence between minimal subsets of the projective space. There is a one-to-one correspondence between minimal subset of the projective space and new stationary ergodic proba on the projective space. You take your semigroup gamma, you look at its minimal subset. It's a closed compact. It contains a stationary measure because it's compact, but it contains one, only one. There is unique ergodicity in each minimal subset of the projective space. In the irreducible and proximal, I had one minimal subset. Here I can have many. In general, I can have many, but each of one contains one and one stationary ergodic probability measure. And conversely, if I take a stationary ergodic probability measure, it supports its minimal. In practice, it may be difficult to understand the minimal subsets because gamma is discrete, etc. There is another bijection outstanding. Actually, this bijection factors by another bijection with the compact orbit in the projective space under the Zariski closure of gamma. Zariski closure of gamma is an algebraic group. It's a closed group in the terminology of Reynolds. So it's a Lie group. Gamma can be discrete, XSL2Z, etc. This is like SL2R. So this is the smallest algebraic group containing gamma. In the case of SL2, and this is a homogeneous, it's a variety, okay? It's an algebraic variety. The compact orbit are algebraic varieties. It's a homogeneous thing. It's not a fractal. The support is a fractal. I mean, it supports a fractal, but I'm saying that this fractal lives in an algebraic complete variety. And each compact orbit of your Lie group supports one and one stationary measure. Example. SL2Z. What is it? Zariski closure? It's SL2R. SL2Z is not stuck in any algebraic group. What are its compact orbit in P1? It acts transitively on the P1. So one orbit, one compact orbit, which is P1 of R. So one stationary measure. So I think it's time, right? Okay.
Do we have any further questions for the speakers? No.
You.
Lecture. So oftentimes when you sort of study the situation and you find out that you're